Manometers. Oh, wait. No. Manometer, not phenomena. Manometers. Manometers do not measure atmospheric pressure. They're not the same thing as barometers. They do a different thing. They measure the pressure of just an individual gas sample. So if I've collected some gas, somehow I may be able to use a manometer to measure the pressure of it. And a manometer looks like this. This is an open-end manometer. It's open-ended because this area here is open to the atmosphere. If this were closed, we could do that as well. Closed-end manometer problems are much easier to do. Well, this will make more sense after I've explained all this, but I'll just say it now. If you encounter a closed-end manometer problem, most of them are open-end, but if you get a closed-end manometer, just measure the difference in heights, and that's your answer. And that's all there is to it. But that'll make more sense after you've seen this long, complicated explanation of how to do an open-end manometer problem. So I have a gas sample. The gas sample is going to be inside of this chamber, and it's connected to a U-shaped tube. And the U-shaped tube has mercury in it. And as you can see here, the mercury is not even on the two sides. It's not even on the two sides because the sample is pushing the mercury down the column on the left. However, air pressure, atmospheric pressure, pushes mercury column down on the other side. And so they're both pushing. The air pressure is pushing on the right, the sample pressure is pushing on the left. And you can tell, since they're both pushing down, one of them is winning. One of them is better at pushing than the other, and it is the... Don't want to give it away. It's very exciting. The suspense is killing me. I hope it lasts. One that is greater is, of course, the atmospheric pressure, because it is pushing down better than the sample. They're both pushing down, sample's losing. So the atmospheric pressure in this case is greater. So everything we do in this problem will involve the atmospheric pressure being greater. If it had been the other way around, if this column had been taller than the left column, then we would have to do something slightly different at the end. So the first question we want to ask is, by how much is it greater? What is the difference? Well, it's that much. It's that much greater. The air pressure is that much greater. Well, what is that? Well, we can go in and we can measure the heights of each of those columns from the zero line there at the bottom and subtract them. Subtract the difference. Subtract them, you get the difference between them, and that difference in heights equals the difference in pressures, because as we know, lengths of mercury columns can be used as a pressure measurement. So let's just make something up. Let's say that there are 32 millimeters difference, 3.2 centimeters difference between the two columns. We're just making that up here. The problem might say that, or it might tell you each height of each column and you'd subtract them yourself. That's not too difficult. So we know that the atmospheric pressure is 32 millimeters more than the sample. That's what we know, but we don't know what the sample is. However, we could use this information if we knew the atmospheric pressure that day. Say if we owned a barometer, we could figure this out, couldn't we? So here's what we know. We know the atmospheric pressure is 32 millimeters more than the sample. And so we know that the atmospheric pressure is the sample plus the difference. We know that. We know that the atmospheric pressure is more, so it's going to be more than the sample by the difference. So we can use this formula, by the way, if what? Well, not for this problem. If the sample had been greater, we would use that. So we add the difference if the atmosphere is winning. We subtract the difference if the sample is winning, if we use this formula. So how are we going to do this? Well, let's plug in what we know. Let's go ahead and measure the atmospheric pressure. Let's get a barometer and measure it, and let's pretend in our imaginary example that the air pressure is standard on this day. So that is 760. Well, our sample is what we want, and we know that the difference is 32 because we measured that. Well, we can solve this. We can solve this by subtracting 32 from both sides. So 760 minus 32 is the pressure of our sample, which is 728 torr, or 728 millimeters of mercury. What did I write down there? There we go. And there you go. That's how you would measure the pressure, air pressure of a gas using a manometer, using an open-end manometer. And like I said, a closed end would just be the difference. There wouldn't be any adding or subtracting to it. So these get a little confusing to some people. Every problem's a little different. What you got to do is just use common sense and say, well, this side is higher or lower, so that side must be pushing more, so this number has to be this much bigger than that number, and measure the difference. And that's how you're going to get those. But be careful. Notice that we used similar units. Everything was already in millimeters of mercury before we had subtracted. If a problem had given us the standard pressure in, or that it wasn't standard, if it gave us the overall atmospheric pressure in atmospheres or kilopascals or anything else, we would have had to convert before we subtracted, or else we wouldn't have gotten the right answer. So remember, anytime you subtract or add values, they have to be in the same unit.